Hello, AP Stats. Welcome back. This is the part 2 of the chapter 6 review for the first one. We're starting from question number 17, and in this video, we will wrap up towards the end. So let's get started with number 17 right away. We're drawing a card from a standard deck of cards of 52. We observe the card and replacing the card. Very important. Count the number of times you draw a card in this manner until you observe a jack. Now, remember that magic word we call until? This means that, it's not binomial because the number of trials is not fixed. You're constantly doing it until you observe a jack, so which means it's going to be a geometric probability distribution. Is a binomial distribution reasonable? No, because trial is not fixed. And it's just as simple as that. For 18 and 19, I will have to say it's probably the two most confusing questions because they don't really tell you what the probabilities are. However, if you were to simply just take a look at the context and just assume these probabilities, because every single event has, to a certain degree, to a certain degree, a probability. So for 18, for example, the pool of potential jurors for a murder case contains 100 persons. Okay, so it seems like N is fixed. Chosen at random from the adult residents at a large city. Each person in the pool is asked whether he or she opposes the death penalty. So it seems like it's either a yes or no situation. We are trying to see if a binomial distribution is reasonable. So it seems like B is checked. For I here, remember for I, it's independence. One person's answer could somehow potentially influence the second person in the line to give, or just the way that they could influence other people's answers. So in order to avoid that, we're gonna check for the condition that allows us to assume independence. And what is the formula for that? Well, it's the 10% rule. So 0.1 n, that has to be greater than the sample size that's provided for us as 100. So do we have enough evidence to believe that there is more than 100 persons or from the adult residents of a large city? Is there good enough reason for us to assume that the capital N, the population of the residents of the I would like to say then adult residents of a large city, the population of that, is that greater than 1,000? Well, where's 1,000 coming from? Well, I just divided both sides by 0.1. So N is greater than 1,000. Yes, I believe that the population of any large cities with good amount of people should be way past over 1,000, tens of thousands of people at the very least. So because of this condition, even though we're not sure if one person's answer influences the other person's answer, we can assume independence because of this condition. Now, N is fixed, like I said, and S, the probability. Now, here's the main problem that I was also very confused about. The probability of the people who's saying yes and people who's saying no, I mean, it really just depends on like how each person really answers these questions. It's not like the probability here is just fixated as 50% or 20%. It doesn't really say that. Now on the answer key, I know it says that it's binomial and because of the 10% without replacement and all these things, but in all honesty, I cannot personally tell you what 18 should be because same probability has to be given to us, and I do not know what the probability should be. They all have opinions, I think, whether he or she opposes the death penalty. So it's not like probability is fixed. So 18, I have to say, if I were taking this test without knowing the answer choice, I would have to say no, it's not binomial. But I know the answer key says yes, and I can't really give you a clear explanation for this. Probably if someone could help me out with this during the class, that would be much appreciated. Number 19, Joey buys a Virginia lottery ticket. Now this, I believe that there is some probability that is existing out there. Like it's 1 out of, I don't know, I'm just making up this number up, like 1 out of 10 billion chance or something like that. So there is a probability that Joey could win a lottery, right? X the number of times in a year that he wins the prize. Now, this just skimming through doesn't provide you any singular numbers whatsoever. First of all, B is checked. Either Joey wins or not. So win or lose. Okay, that's easy to figure out. Independent. Each lottery ticket's chances are independent from one another, so that should be fine. Or you can also do the 10% rule, and here, then you might be wondering, well, what in the world is N? Well, if you're talking about buys a lottery ticket every week per year, that's 52. I'm sorry, the lowercase n should be 52. One ticket per week, and there's 52 weeks in a year. So that should be 52. So it is fixed. The same probability here. Now, this is, again, like, it's not stated. Like, what is the chance of Joey winning the lottery ticket? That's what really bugs me about this question. But comparing this to 18, like 19 is talking about a Virginia lottery ticket, which should be fixated like on the spot. Like the chance of you winning a lottery for this particular thing should be fixed. So even though it's not stated, we can assume that the probability should be fixed for every lottery tickets out there, the chance you win or not. So we're going to assume that's also going to be true. So yes, this is going to be a binomial situation. All right, number 20. A fair coin is flipped 20 times. Determine the probability the coin comes up tails exactly 15 times. Fair coin means it's 1 out of 2. Probability, independence, heads or tails, binary outcomes. And n is fixed, so it's bins, so it's binomial. And if I want to find out exactly 15 times, it's binomial PDF, right? So we're going to go to binomial PDF here. And we are doing, sorry. So binomial PDF, the number of trials is 20, chance of success is 0.5, and the x value is 15. And the answer for 20 should be, yes, 20, 0.5, 15, 0.01478. Part B, find the probability that the coin comes up at least 15 times as tails. Okay, so at least 15 times means pretty much the same thing as what we have done before. We're going to do binomial CDF. We're going to go up to 15. So 20.5, 15. So that is about 0.994, 99 times, at least 15 times. Oh, my apologies. At least 15 times means 15 or more. So 15 or more means I actually have to change this to 14. Why? Because I don't want to include the 15 in the ones that I'm subtracting away. So what if I want to find out at least 15, that means 1 minus probability of the binomial CDF up to 14, because it's 15 and above, which means I want to get rid of the rest starting from 14. So I do 1 minus the binomial CDF version of the 14 there. So the answer for this should be 0.020694. And for part B for 20, yes, that should be correct. Part C, find the mean of the standard deviation for the random variable. So because this is binomial, I know it's NP 1 minus P square rooted. 0.5 times 20. That should be your expected number of times that the tails will appear if you flip the coin 20 times. And then this here would be square root of 10 times 0.5. So that's square root of 5. So that should be about 2.236. And all of those answers should be fine. Now, the last question, find the probability x that takes the value within 2 standard deviations of its mean. Well, can I use normal distribution here? Yes, you can, because we're talking about n times p greater than or equal to 10 right here. So 20 times 0.5 is greater than or equal to 10. N times 1 minus p is also greater than or equal to 10. 20 times 0.5 is also greater than or equal to 10. Now, what in the world am I doing for this? This is the rule, the large counts conditions that allows us to assume normality. It should be in your notes. Sorry, that's N for normality. So because these two conditions are checked, yes, both of them has to be checked off, which means I can go back to my chapter 2 things and do normal stuff, normal CDF. The mean here, 2 standard deviations away from the mean. We know the mean is 10 from part C. Standard deviation is 2.236. Find the probability that x takes a value within 2 standard deviations. Well, 2 standard deviations, because it's a normal probability distribution, we can actually use empirical rule and say that's 95%. But just to be sure, we'll use our calculator and then we're going to go to second vars, and then go to our good old friend, normal CDF. The normal CDF asks you for the lower and the upper boundary. Well, the lower boundary should be 10 minus 2.236 minus another 2.236. So 10 minus 2.236 minus 2.236. And then upper should be 10 plus 2.236 plus 2.236. And then the mean will be 10, and the standard deviation is 2.236. And then it should give you about 95%. Yes, you can actually add and subtract inside the normal CDF too. 95%, or you can call it 95.44%, but you can see how they're very close to the empirical rule. Just FYI, empirical rule 68, 95, 99.7. That's the first, second, and third standard deviations away from the mean. Don't forget that, please. All right, so now that I have that, let's go to 21. A headache remedy is said to be 80% effective. An investigator tests this remedy on 100 randomly selected patients suffering from nervous tension to find the random variable being measured. We're talking about if effective, right? Curing headaches. Okay, or we're trying to find out number of cured patients who have nervous tension. So that should be much more appropriate. So X should always represent the number of physical sense, what we're trying to count or what we're really interested in. What kind of distribution does X have? Well, it seems like we have P, same probability, 100, so that's N. You either cure or not cure, and it's independent because each patients are different from one another, so their probability of being cured or not is independent from each other. Great. So what kind of distribution? Binomial. Calculate the mean and the standard deviation. Getting pretty old at this point. Mean, standard deviation, let's figure those out. So that should be 0.8 times 100, so that should be 80. This one should be 80 times 0.2, so that should be 4. Determine the probability that exactly X is within one standard deviation of the mean. If we use the normality formula once again, n times p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10. Make sure you check for those conditions. We've already saw that n times p was greater than or equal to 10 from part C. So what about the other one? Well, we take the number of trials and multiply by the chance of failure. That should still give you more than 10 because it's 20. So check. Normality can be assumed. If it's one standard deviation from the mean, that's the empirical rule. So we're talking about 68% of the time, it's going to be within one standard deviation from the mean. Use a normal approximation to find the area. Using the normal approximation means to use the normal CDF. So go to second vars, we're going to go to normal CDF, and how lovely were they to give me those two numbers, 72, 88, with the mean of, I believe was 80, and a standard deviation of 4. Very nice numbers. And we have 95.44%. Seems that this was the same exact answer as the previous one that we did. That was 2 standard deviations away. Your results should be very close to the empirical rule. Why is this true? Because we can assume normality due to large counts conditions. NP greater than or equal to 10, and 1 minus P is greater than or equal to 10. So really, this condition allows us to assume normality, and anything that you do with normal CDF, normal PDF, those are all going to be fine. And so that's why it's very important for you to check for these conditions. Can you assume normality, even though it's very unclear as to how it's going to look like? Okay, so for number 22, compute and interpret the mean of the standard deviation. Let's go back to our good old friend table once again. Stat edit. We have to clear all the list, even though it looks quite similar. Okay, so we're going to clear that list. 0, 1, 2, 3. So we're zooming into this, and we're looking at 0.4, 0.3, 0.2, and 0.1. And then second, or stat calc, one var stats. Good. So we have the mean is 1, and the standard deviation, wow, that's also 1. Kind of nice. Did I do something? Nope. It's all correct right there. Okay, so suppose we also randomly select a phone that may require repairs over time. They have their mean and the standard deviations respectively as 2 and 1.2. So what is the mean and the standard deviation of the total number of repairs, which means they're simply just asking me to add those two things up. So the mean of the combined variable is the mean of the MP3 players and the plus the mean of the phones, which is 1 plus 2 is 3. Now, the standard deviation of the combined variable is the variance of the two. So we're going to call the standard deviation of MP3 squared plus the standard deviation of the phones squared, and then we're going to square root that. So square root of 1 squared plus 1.2 squared. So using my calculator, so 1 plus 1.2 squared, square root that answer. So that should give me 1.56204. So that should be the standard deviation, and that gives me the answer. Yes. Part C, $15 and $25 for each MP3 and each phone. So we want to find out the mean and the standard deviation of this. Now, when you multiply, because I mean, it's obvious, each of the number of MP3 players and phones that you repair, you have to pay these amount per unit. So when you multiply, yes, your mean and the standard deviation get affected. So your cost would be $15 times the mean of MP3 plus the $25 times the mean of the phones. Now, you have to take these two separately because they have two different price or two different costs. So 15 times 1 plus 25 times 2, that should give you $65 as your average cost to repair the phone and the MP3 on average. And the standard deviation of the combined, we are going to do the same thing. 15 times the standard deviation, which is, I believe it was 1. And then the standard deviation gets multiplied by 25, which is 1.2. Now, you have to be careful that this entire thing has to be squared in order for you to find out the variances. It's not variance multiplied by the price. It's the standard deviation multiplied by the price and then squaring it. So plus and then square rooting it. That should be the final answer. So that's 15 squared, 25 times 1.2 and squared. So what I get is square root of 225 plus, that should be 900. So plus 225, square rooting that answer, you get $33.54 as your standard deviation. Okay, and checking the answers, I believe we should be okay. Okay, so I think this should be our final, FRQ of the first review packet. Mr. Voss and Mr. Call bowl every Tuesday night. Over the past few years, Mr. Voss's scores have been approximately normally distributed with the mean and the standard deviation as provided. During the same period, Mr. Cole's scores have also been approximately normal with 230 and 40. Now, what they're asking is, what is the probability that Mr. Voss scores higher than Mr. Cole? So I'm just going to call the mean of the Mr. Voss as V. Well, I'm sorry. I'm just going to call the variable V as Voss and C as Mr. Cole's. What we want to find out is V greater than C. That's what the notation of the probability that they use also for the answer key as well. So how in the world are we supposed to figure this out? Well, we know it's normally distributed. So we know we're supposed to be doing something with normal CDF. But what in the world is the mean and the standard deviations for all of this? Well, it turns out because we want to find out Voss's scores being higher than Cole, we want to subtract these two things. If you subtract those two scores, that's the combined variable question. So we want to find out the mean of V minus C, and we also want to find out the standard deviation of V minus C, combining the two random variables. So the mean of Voss is 212, and the mean of Cole is 230. So it's 212 minus 230, because it's simple as that. When you're combining the mean, just add or subtract as given. That's negative 18. Now for standard deviation, the standard deviations formula never changes. They will always add. So it's square root of 31 squared plus 40 squared. You do not subtract those two numbers. So 31 squared plus 40 squared, square rooting that answer gives me 50.606. These two will be my mean and my standard deviations that I would like for us to use for finding out this, Mr. Voss scoring higher than Mr. Cole. What they want is V minus C to be greater than 0. Because if that is true, Voss has scored more than Cole. That's what this means. So if I were to draw a normal distribution curve with the mean of -18 and a standard deviation of 50.606, somewhere over here, there's got to be a value 0, and you want to figure this out. You want to shade on the right-hand side because this represents Voss being greater than Cole because the score difference is higher than 0. Okay, so we have the picture ready. Now we have to put this into our calculator. So second vars, and we're going to do our normal CDF. The lower boundary here should be 0, and the upper boundary should be 99999 because it's going all the way infinitely that way. With the mean of -18 and a standard deviation of 50.606, the chance of that happening is 36.10%. And the answer key also, I believe they say the same thing, 0.36. Okay, so again, it's a normal distribution question in much more complicated format. It's combining random variables. That's basically what it comes down to, using those two formulas provided and putting into a normal CDF. Yes, 23 was actually a bit tough, along with 18 and 19. Finally, multiple choice questions again. Binomial and geometric probability situations share many conditions. Yes, they do. They share B, they share I, they share S. They do not share N because geometric means that the N is not fixed. So we're really looking for the answer choice that has everything to do with number of trials. And I think it should be C, right? The focus of the problem is the number of success in a given number of trials. The number of success for binomial can be multiple. Like it could have 2, 3, 4 success. Geometric, you only have 1 success because you keep on doing it until you get that 1 successful attempt. And that's it. So it should be C. A set of 10 cards, 3 red cards and 7 black cards, shuffled. You turn the cards over one at a time, beginning with the top card. Okay, let Y be the number of cards you turn. Observe until you observe the first red card. The random variable Y has which of the following probability? So you might think, oh, I see the word until, it's geometric. But the problem here is that those 10 cards, like if I were to just draw this out, you draw one card out and you look at it, the chance of the second one being red changes dramatically because your denominator number is now out of 9, then your denominator number is out of 8. Remember, for a geometric, same probability has to still exist. So geometric probability distribution with the success of 0.3, it's not possible because the next one could potentially be 3 out of 8. It's not binomial, it's not normal because we can't assume that. N times P, N times 1 minus P, you can do that yourself. It's not going to work out. Therefore, it's none of the above. 26, which of the following is a true statement? The binomial setting requires that there are only 2 possible outcomes, while the geometric setting permits... Okay, first of all, geometric also has binary outcomes. It's either yes or no, success or failure. A geometric random variable takes on integer values from 0 to n. That's not correct because you have to have at least 1 try of success. So you have to start from 1 to n. If x is a geometric random variable and the probability of success is 0.85, then the probability of distribution x will be skewed to the left since 0.85 is closer to 1 than to 0. So what in the world is this talking about? For geometric random variable, guys, always you got to remember, geometric is always skewed to the right, no matter what it is, because the chance of success at the beginning should be very relatively high. But then as you do more and more tries, because the chance of failure keeps on getting increased by a factor and raised to the power of, like k minus 1. So as k keeps on increasing, the chance keeps on getting diminished because when you take a fraction number and constantly multiply by other fraction numbers, it gets tinier, tinier, and tinier. So it's always skewed to the right. An important difference between binomial and geometric random variable is that there's a fixed number of trials and the number of trials varies. I mean, that is a perfect example of what binomial and geometric definition is, or the difference between the two is. The distribution of every binomial random variable is skewed to the right. Nope, it's always going to be symmetrical, or in most cases, but it's accepted that it's going to be symmetrical. So it's D. All right, 27. A college basketball player makes 80% of her free throws. Suppose this probability is the same, and the free throw attempts are independent. The probability she makes all of her first four, oh, that's easy. 0.8 to the power of 4 times 0.2. That's all you got to do. So the first four, you make it. The last one, you don't make it. It's B. A college basketball player makes 80%. Seems like the same thing, but and the free throw are independent. The expected number of free throws until she makes her first, okay, that's geometric, and okay, the average or the mean number is given to us in the formula as 1 over p. So 1 over 0.8 is 1.25. Suppose that 40% of the cars in a certain town are white. A person stands in an intersection waiting for a white car. Let X be the number of cars that must drive by until another geometric question. Probability of X less than 5. Let's go to our calculator. X less than 5 is same as X less than or equal to 4. So what I'm going to do is second vars, geometric CDF, 0.4, and then 4. And then it's 0.8704. And yes, that's the correct answer. The expected value of X for geometric is always 1 over P. So 1 over 0.4, 2.5. That was pretty simple. A poll shows 60% of the adults in a large town are registered Democrats. If the reporter asks adults on the street random, what is the probability that he will find a Democrat by the time he has stopped 3 people? So we want to stop until the third person becomes a Democrat and the first two are not Democrats. So that is 0.6 here, 0.4, and 0.4. Or you can, yes, it's a geometric PDF situation. You can do the same thing. It's going to give you this same number. So 0.4 to the power of 2 multiplied by 0.6, or I can do second vars geometric PDF because I want to stop at exactly the third person. Chance of success, 0.6. Going to give you the same thing. 0.096 should be the answer, therefore. On average, how many people will the reporter have to stop? 1 over P, 1.67. Okay, I'm going to fly through these really quickly. Using the following information about 33 and 34, on average, how many people do you expect you will have to ask before you find someone? So here, I think, suppose that 16% of drivers carry jumper cables in their trunk, and you want to constantly ask again and again until you actually find someone that can lend you a jumper cable. So this is 1 over P because it's geometric situation. Number of trials is not fixed. So 1 over 0.16, 6.25. You're going to give up and call a tow truck if you don't find jumper cables by the time you've asked 10 people. So it's probability of X is less than or equal to 10. But if it exceeds more than that, you call the tow truck. 1 minus P of X is less than or equal to 10. Now this, I'm going to rely on our good old friend, geometric CDF, with P being 0.16 and X value being 10. So when you do that, you get about 82.5%. That's the time, that's the chance of you actually running into somebody with jumper cables by the time you reach 10%. So 1 minus that answer means anytime above the 10th person, you're going to call the tow truck. The answer here, therefore, should be B. About 17.5% of the time, you will end up doing that. Last question. Which of the following are true statements? Okay, so for question number 35, this is going to be a little bit more elaborate because we have Roman numeral questions, and one says the histogram of a binomial distribution with P of 0.5 is always symmetric. So guys, one thing you need to understand about binomial distribution is that when you actually plot the histogram for 1 trial, 2 trial, and 3 trials, and so on, and I can show you this myself here. Yes, the number of trials is not fixed, but let's just give it a number. Let's just say the number of trials is 10, okay? You can just make up any numbers. It doesn't matter. But 10 is a good number for us to use. So second bars, and let's say I do binomial PDF, right? Number of trials is 10, chance of success is 0.5, and the x value, it starts from 1. And notice how the value of this is really small, 0.009. Now, when I keep on increasing this number, notice what happens to the probability. It goes up to 4%, then it goes up to 11%. When you keep on doing this, eventually what it turns out, it reaches the highest number somewhere in the middle. Then it slowly starts to plateau away. See, now it goes down. So here at 5, you hit the highest mark at 24%. Then you start to go down again. Now, obviously, I can continue down the trend, 7, 8, 9, 10. But you see why for every binomial distribution, more or less, it will shape its shape will turn out to be in a normal, in a very similar setting into a normal distribution. So 1 is absolutely true. I'm going to eliminate C and E because of that. The histogram of a binomial distribution with P of 0.9 is skewed to the right. Now, once again, even with 0.9, it doesn't matter. Binomial distribution for histogram, I can change this as 0.9, and then I can still show you like what happens. Now, you can see how in the very beginning, all of the probabilities in for binomial PDF were 3, 4, 5, like they're very, very small. So 1, 2, 3, 4. I'll just start from the very beginning. So let's say I do 0.9 as the probability of success. I mean, that is really close to being 0. Now, if I go up to 2, still very, very small in terms of their probability. 3, 4, and 5. So what am I trying to say is that all of these probabilities are really just close to being 0% or like 0.1% at 5, right? But when you go up to 6 and 7, it's going to rise up like crazy because now your chance of success at the higher numbers is going to increase in terms of the formula. When you multiply them, it's going to get more and more increased. So if I were to go up to like, let's say 7, perhaps, now you're up to 5%. Then at 8, you have a whopping 19%. And at 9, you get 38%. So it's huge on the right-hand side of the equation or right-hand side of the graph. So this is skewed to the left distribution. So therefore, 2 is not going to be true because it's not right. So D is out and A is out. So it seems like our answer choice will be B. But just for the sake of going over this, I'm going to tell you right now 3 is absolutely true. For geometric setting, for all of you guys, remember it's P to the K minus 1. Oh, I'm sorry, 1 minus P to the power of K minus 1 times P. When you have low number of trials, like for example, if K is 1, you just mark down P, whatever your chance of success was. So whatever your chance of success was, you write it down. Then you multiply by another fraction because you need to have a chance of success and a chance of failure. Now, remind you that these two are going to be fractions, and whenever you take a fraction multiplied by a fraction, it gets smaller and smaller and smaller and smaller. And so geometric is always skewed to the right distribution here. And that will never change. It will always be decreasing when the value keeps, like the more trials you do, the chances of each of them happening just keeps on getting diminished after one another. Just keep that in mind. So that should be B, and that should wrap up the first review of chapter 6. Whew, that was a lot. Hope this video really helps you guys out, and please use this as a study material. And I'll see you guys next week with reviews and frappies and the test on Thursday.